Hi guys, just wanted to give you a quick synopsis of some of the high points of tomorrow's reading assignment. Tomorrow we reach what I think is probably the funnest and most important part of what we're going to do in this course, and that's looking at the interaction of fields and matter. Granted, it's static fields. Next semester we'll look at dynamic fields and their interaction with matter, and that's the interaction of light and matter, and hence optics. But this is the first step. So we take everything we've learned so far and we apply it to the interaction of those fields with material objects. And we start by taking a look at the resulting polarization. As illustrated in your text, if we take a neutral atom and we put it in an electric field, the electron cloud of that neutral atom gets displaced a little bit. And so here would be my field, in this case pointing from left to right. Now we'll start our discussion of the interaction of fields and matter by looking at the simplest case, single electron orbiting around a single nucleus. This is typical of how physicists approach problems. We simplify things and then we start making them progressively more complicated, and the math gets progressively more messy, and often or usually or always becomes unsolvable. So we introduce approximations to make things solvable, and then we start making those approximations more and more accurate. And as we make them more accurate, the math gets messier and more difficult to solve. It's just standard approach. And so we start looking at single electron, so the hydrogen atom. Apply an electric field to it, electron cloud gets displaced. We say that the atom gets polarized. As a result of that, you can see that there's going to be now a dipole moment to this polarized atom, because the center of charge for the electron cloud is now here, and the nucleus, if it's part of some lattice, it doesn't move. Either way, the electron cloud is displaced off center, and so it picks up a permanent dipole moment, or an induced dipole moment. I shouldn't say permanent. Now has an induced dipole moment. Generally speaking, the dipole moment that results, or the polarization that results, is proportional to the inducing electric field. And we write that proportionality as P is equal to alpha E, where this alpha is the atomic polarizability of our atom. Turns out that the situation is considerably more complicated than what we've illustrated here. And so we usually have to write out this polarization in a Taylor series expansion in the powers of E. And so it looks something like this, where beta would be the second order polarizability, gamma would be the third order polarizability, and so on. For our first pass through, we're going to focus in on the linear term. And so this polarization, atomic polarization, would be equal to alpha times E, where alpha is the polarizability. It's a proportionality constant. But we also know from the last chapter that this polarization is also known as the dipole moment. P is equal to Q times D. And so we can use these two formulas to determine theoretically a value for alpha and compare it to a measured value. And for a hydrogen atom, it comes relatively close. For anything other than a hydrogen atom, the more complicated your atom gets, the worse this equivalence becomes. And that's because we are missing these higher order terms, which are increasingly appreciable. In addition, if we start throwing in more electrons, the polarization, this alpha is no longer just a constant, but as you saw in the reading, it becomes a tensor, especially if you have a molecule. Molecules, different atoms have different electronegativities, and so the polarization will occur easier in some directions than in others, which you see here in equation 4.3. An important thing to remember from the reading, when you place a material in an electric field, it will induce a charge separation in that material. That charge separation will then create its own field. Chapter 4 is about calculating the fields from polarized materials. Well, that field results from basically two separate mechanisms. One is the polarization that we just talked about, the charge separation. But a lot of molecules, because of the electronegativities differing between the individual atoms, will have permanent dipole moments. And those permanent dipole moments, if you immerse that molecule in an electric field, experience a torque. And that torque will cause the molecules to rotate. Even if the molecule doesn't have a permanent dipole moment, because of its symmetry, you'll still get an induced dipole moment. And the induced dipole moments will then be rotated. So you've got two things happening when you put a material into an electric field. You induce dipole moments, which are then rotated, and permanent dipole moments are also rotated. The last thing you need to worry about, the last thing we'll take a look at, and just very briefly, when you place a material into an electric field, if that electric field is non-uniform across the diameter or the radius of the molecule, then you don't have symmetric forces. There'll still be these forces that cause the dipoles to want to rotate. But if the electric field is stronger here than it is here, or vice versa, then you'll have a differential force which will cause that molecule to want to migrate or diffuse through the material. To first order, that diffusive force is given by the expression you see in your text. This is extremely important for this being able to calculate this force accurately. If you're looking at molecular diffusion for, let's say, concentrating uranium, you want to know how fast the molecules will diffuse. Subcutaneous drug delivery, you put a drug into a gel patch, and then you put that patch onto your arm. You want that drug to be delivered over a certain period of time. Too fast and the person dies. Too slow and the drug doesn't have its desired effect. And so you need to be able to calculate these forces to determine the diffusion rate of the drug. In terms of the torques and the polarizations that are involved, that's a big deal for any type of materials research. The way we know about something at the molecular level, one of the big ways is shining light through it and take a look at how the material changes the light from on the way in to on the way out. By looking at those changes, we can then back solve and say, oh, well, because the light's polarization changed by this much, and because its intensity changed by this much, and these wavelengths were absorbed out, we know it has this structure and this chemical makeup and so on and so forth. Well, the only way we can make those conclusions is if we can understand how electric fields interact with matter. So this is huge. Personally, I think this is the most important chapter that we'll cover in the text. So please read over section 4.1 and come prepared to do a couple problems tomorrow. Have a good night.